Howdy students, this is going to be a video that covers aqueous solutions, polar versus nonpolar, and electrolyte formation. So aqueous solution has the word aqueous, and specifically it has aqua, which means water. So these are going to be solutions that contain water. And specifically, they are going to be solutions that contain water as a solvent. And so with that, we have three different terms: solvent, solute, and then, of course, the solution itself. So the solvent is the dissolving medium, or what does the dissolving. Solute are the particles that are actually dissolved in the solution, or what gets dissolved. So would the salt or the water be the solute in a salt-water solution? Well, if we know anything about salt, it dissolves in water. So the salt would be the solute, and the water would be the solvent. Water is known as the universal solvent in most cases. So there's a diagram down here. If we have salt, over time, the solvent, water, begins to break down the salt in a process called solvation. So solvation is the process that occurs when a solute dissolves in a solvent. So three different pictures here. We have a cube of salt. And in the first picture, you'll see that the salt is not being dissolved very much at all. But over time, the water begins to eat and actually surround different ions of the salt molecule. And what we get eventually is a complete breakdown from the second to the third picture. If we zoom in even closer, we can actually look at the attractions between the water molecules and the ions. So you'll notice that if we look up here on this top portion, all of the positive sides, the hydrogens, are attracted to the negatively charged chlorine atom, because the hydrogen on the water is positively charged and the chlorine has a negative. So there's an attraction there which helps rip apart the ions. On the other hand, if we look down here, we will see that the negative oxygens are actually pulling close to the positive sodium. And if I draw that out, I would have a negatively charged oxygen, positively charged sodium, and once again, there's an attraction between the two. We call these solvation spheres. When we dissolve compounds in solvents, solutes within solvents, we have a term that we like to say, like dissolves like. Polar substances dissolve in polar solvents. So, for instance, water, because water is polar, would dissolve things that are polar and ionic. Nonpolar substances dissolve in nonpolar solvents. For example, gasoline would dissolve things that are nonpolar because gasoline is nonpolar. So if you want to summarize, if you have a polar solvent, that will dissolve polar things and ionic. If you have nonpolar solvent, it will only dissolve nonpolar solutes. So some examples of polar substances, let's write it over here, would be things like water, sugar, alcohols, and then specifically we'll see NH3 as well, which is ammonia. Things that are ionic, anything that has a metal with a nonmetal, salt, anything that forms ions in solution. And then nonpolar examples would be things like gasoline, anything with carbon and hydrogen bonds, Things like methane, butane, kerosene, anything that is perfectly symmetrical would be nonpolar. So here's an example. Ethylene glycol, this is a type of alcohol. And because alcohols are polar, we would expect this to fully dissolve within water. And then a hydrocarbon are things that have carbons and hydrogens, which are generally nonpolar. You'll see that there is a line of miscibility or immiscibility, which does not dissolve. So oil and water would be a good example here. So if we're using this information, write soluble next to the compounds that would dissolve in water, which is a polar solvent. So gasoline is a nonpolar substance, so that would be non-soluble. Salt, NaCl, that's an ionic compound, and we know that ionic dissolves in polar, so we're going to say soluble. Alcohol is a polar compound, which would dissolve in other polar solvents. And then oils are non-polar by nature. They do not mix, so that would be a non-soluble. And the last thing we're going to talk about here in this video are electrolytes. Some compounds, when they dissolve, can conduct an electric current within an aqueous solution or in a molten state. And the word molten here means liquid. So these are called electrolytes. You'll see the word electro because it can conduct an electric current. To do this, you need ions. There have to be some sort of ion present. So when we hear electrolyte, a lot of times we think of Gatorade. These would include all ionic compounds. So the reason Gatorade is an electrolyte is because of how much salt is within the solution. Some very polar molecules dissolved in H2O, such as ammonia in H3, they can also conduct electric current sometimes. We can have non-electrolytes, which are compounds that do not conduct an electric current. These would be molecular compounds or organic compounds and nonpolar compounds. So remember, molecular compounds, same thing as covalent. That'd be a nonmetal with a nonmetal like CO2. Water by itself. Anything nonpolar that has symmetry, like oil and gas. So in class, we do a demonstration where we actually conduct electric current with a light bulb to test out different aqueous solutions to see if they can conduct current. And what we would find is that there would be a non-electrolyte with something that there are no ions present. If there is partial dissociation into ions, so a small amount of ions, we can have a weak electrolyte. But if all the ions are present, we can have a strong electrolyte and the light bulb would light up 100%. So we need to know the difference between strong and weak electrolytes, and that's where we're going to finish here. In a strong electrolyte, nearly all of the ions dissolve. So what I tell my students to write are 99% ions. The solvent has done a good job. The solute has also done a good job at breaking apart to form a solution. So these are your strong ionic compounds like sodium hydroxide, which breaks apart into Na plus and OH minus. HCl, which breaks apart into H plus and Cl minus. And NaCl, which is Na plus and Cl minus. These are all great electrolytes. And then you have weak electrolytes, where we only have a small amount of ions dissolved. And what I tell my students to write down is like less than 1%. So there's some charge, but not a whole lot. There are some ions, but not a whole lot. Distilled water, ammonia, acetic acid, these are all generally polar compounds. Acetic acid would be HC2H3O2. Distilled water, water is polar, ammonia, NH3 is polar, acetic acid can be considered an ionic compound because of the breakup of H plus and C2H3O2, but because it doesn't break up 99% in solution, it is a weak electrolyte. So how do we form electrolytes? Well, we have to dissolve them in water. If we have a compound by itself, it's not going to create any sort of ion or charge. So for instance, if ammonia is with water, it can break apart to form NH4, which is ammonium and hydroxide, and we get these charged particles. Hydrochloric acid in water breaks apart, H plus and Cl minus. One of those H pluses joins the H2O to form H3O plus, which we call hydronium, and chlorine forms chloride, which is an ion.